Okay, welcome to your video for Friday, November 7th. The first part, I'm going to go over this worksheet that y'all did yesterday in class, and the second part is we are going to do the 5.3 Day 2 notes. So everyone get out your worksheet from yesterday that you already should have turned into Google Classroom and get out another color pen or a colored pencil or something and correct your worksheet as I'm going through the video. You should not just be sitting here staring at the wall, running out the clock. Correct your worksheet as I go over it. So 2 mutually exclusive events. These are 2 events that cannot occur together. So the intersection is 0. So that was a Venn diagram. It would be 2 circles, not touching. Independent events. Knowing the outcome of one does not help predict the other. So, the probability of A given that B has occurred is just the same as the probability of A. Knowing that B has occurred does not change the probability of A. The probability of A is just still whatever it was before. And then also we have that property that the probability of A and B is the probability of A times the probability of B. 2 independent events, A and B, exist such that the probability of A is 0.5, the probability of B is 0.2. So the probability of A and B, that's 0.5 times 0.2, which is 0.1. The probability of A given that B occurs, well, that still is just 0.5. Doesn't matter that B happened. The probability of A given that B complement occurs, it still is just 0.5. The probability of A or B, the union. So I'm going to do a little Venn diagram for this. So the union means we are looking at this guy, and this guy. Okay, all 3 of those apply to the union. Oh my gosh. The intersection is just this little middle guy. So I know that A is 0.5 in total and B is 0.2 in total. We already know that intersection is 0.1. So the rest of the A circle must be 0.4. Now this whole circle is 0.5. That's the probability of A. The rest of this circle must be 0.1 because now this whole circle adds up to 0.2. That's the probability of B. So the union is just all those yellow pieces added together, which is 0.6. And the probability of B given that A occurs, well, that's just 0.2. Knowing that A has occurred does not change the likelihood of B occurring. Suppose 10% of adults belong to health clubs, 40% of those health club members go to the gym at least twice a week. Probability that a randomly selected adult belongs to a health club and goes there at least twice a week. So whenever I have 2 events and they can do one at a time or both of them, I know I'm going to make a Venn diagram. So 10% belong to the health club. Oh, let's see, 40% of those go at least twice a week. So this is belonging to the health club, that's twice a week. So 40% of that 10 go twice a week. So this is 0.04 and this is 0.06. 40% of that 0.10 goes in the middle. So the probability, what are we doing? That they do both? Oh, it's just the 0.04 right there. A student is applying to different jobs at Starbucks and Dunkin' Donuts. The probability that they'll get an interview at Starbucks is 0.4. Interview at Dunkin', 0.7. 50% of the people who get interviews at Dunkin' also get interviews at Starbucks. So half of that 0.7 which would be 0.35, has to be in that intersection also getting an interview at Starbucks. What is the probability that they will get at least one interview? So at least one interview means, could be talking about these people, these guys, or these guys, all of them. What we're looking for is the union. So we add all those up and we get 0.75. All right, probability of being a senior, 0.22. Driver's license, 0.3. In total, it's 0.36. And we want to know the probability that they are a senior and have a driver's license. So, and we're looking for the middle. So I like to label the three zones X, Y, and Z. And I think about that middle guy as Y. So I know that the probability of being a senior plus the probability of being or having a driver's license, we're looking at in total that union, it's 0.36. However, if I do that, see where I'm circling around here and where I'm circling around here. I just counted the middle zone Y twice. Can't be doing that. We only want to count Y once. So there's my equation to set up. So 0.22 plus 0.3, but take out that middle part that I just counted twice. That equals 0.36, and when you solve, Y is 0.16. And we don't have to bother with the rest of the circle because that is what we were looking for. All right, the answer to this one is A. They are mutually exclusive because you can't do both. You choose one of the two discounts. So they are mutually exclusive, and then the definition of that is the intersection, the probability of both happening at the same time is 0. Okay, this one's really fun. We have independent events. This is a key word right here. The probability of A is 0.3. Probability of A or B is 0.65, and we want to find the probability of B. Okay, here's A. So, I know that all of these together must add up to be 0.65. So, A is 0.3 plus B, but we have to minus away that little intersection part because we don't want to count it twice, equals 0.65. Well, we have an issue. We have one equation and two variables. That means we cannot solve for one unique solution. But we can use this fun little other part that events A and B are independent. This means that the intersection, probability of A and B happening at the same time, is A times B. So that intersection part, that's just what I'm calling Y, kind of for short. So Y is A times B, that middle part. Only because they're independent. So I also already know that A is 0.3. Now I have two equations and two variables. We have a little system and we can solve. So exciting. So 0.3 plus B minus Y, but I'm going to substitute in this equation for Y, this guy over here. I know Y is 0.3B equals 0.65. So 0.3 plus 0.7B equals 0.65, and we get our little calculator, and we do 0.65 minus 0.3 divided by 0.7, B is 0.5. Pretty neat. So the key there is remembering that when A and B are independent, the probability of both of them happening is just A times B. That only is true for independent events. All right, lastly, we have two characteristics in each of these tables, and we know one of them is independent and one of them is dependent. So based on just what you know about the world, you can probably figure out which is which. But we have to mathematically justify and support our answer. So there's a bunch of different ways that you can do each of these. So your method might not have exactly matched mine, but that's fine. There's multiple right ways to get the answer. So here, I looked at the probability of being a female given that somebody is a teacher. So those 22 people out of the 28 teachers. So that probability is 0.79. And then I said, okay, well, what's the probability of just being female? It was 550 out of 1,000, which is 55%. So if you are trying to just think of a random person and guess whether or not they're female, 55% chance that they are a female. However, if you know that person is a teacher, it's way more likely that they are female. So these two events are not independent. Knowing that somebody is a teacher makes it way more likely that they are a female than just knowing that they're one of these 1,000 people. So these guys are not independent. Or as some might say, dependent. All right, then over here, we probably know that brown eyes and not brown eyes are not dependent with your gender, but let's make sure. So I'm going to go kind of the same strategy here. What's the probability of being a female given that you have brown eyes? It's 0.55 because I did that 440 out of the 800. And then we know from before that just the probability of being a female is 0.55. Therefore, they're independent. Knowing that somebody has brown eyes does not make it more likely that they are a female. Okay, so now let's get out our note packet. You can pause the video for a sec if you need to do that. But get out your note packet and then go ahead and do the 2 warm-ups at the top and then play the video again. Okay, so now that you've paused the video and done the warm-ups, does the residual plot support the appropriateness of a linear model? No. That residual plot shows a pattern, therefore the actual data is not linear. Some other function family would be better. All right, one student from a high school will be selected at random. A is the event that they're an athlete. B is the event that they drive to school. So the intersection is 0.08. Let's call that A and B. And the probability of B given A is 0.25. So the probability that they are here, given that they are in this circle, okay? Given that they are in this circle, the probability that they are in the intersection zone is 25%. So that means 25% of this A circle is here. The probability that they have done B, given that they're in this circle, is 25%. So that means 0.08 is 25% of the whole circle. It's a quarter of it, which means the whole circle size must be 32. Okay, general multiplication. What is the probability that 2 events A and B both happen? First example, about 55% of high school students participate in a school sports team. About 6% of those athletes go on to play for some level of an NCAA team. What percent of high school students play a sport in high school and go on to play for an NCAA team? So we're looking out of all high school students. So 55% of high school students are athletes, and then another 6% of those go on to play for an NCAA team. So it's 6% of that 55%, which is 0.033, 3.3%. So it's 6% of the athletes play in college, but 3.3% of the whole high school play in college. So the general multiplication rule is just that probability of A and B happening is that. You multiply them together. So 79% of teenagers use social media. 39% of those teens who use social media feel pressure to post content that will be popular and get lots of comments or likes. Find the probability that a randomly selected teen uses social media and feels pressure to post content that will be popular and get lots of comments or likes. So the probability that they do both of these things we're just going to multiply them. 0.3081. Okay, you can try this one with a table partner for a sec and then play the video. Okay, so now that you've worked on it with your partner and you played the video, what percent of Australian Shepherds registered that year had red coats and tri-patterns? Well, we see 13% of them have red coats. And then, let's see. Oh, the tricolored patterns. There we go. 0.78. Multiply them and we get 0.1014. So that's the percent of all Australian Shepherds who had that, whoopsie, up here, who had that combination. This guy is a black tri. He has black fur and 3 colors. So then what percent of Australian Shepherds had red coats with merle patterns? That would be the 0.13 times 0.22, which is 0.0286. And if you add these together, what do you get? 0.13, because that accounts for all 13% of the dogs with red coats. Coda is a blue merle. She has blue fur. Okay, so that was the general multiplication rule, which is going to kind of help us here, but tree diagrams, we're going to, I don't know, not totally switch directions, but maybe we'll take a kind of a sharp right turn. Not a total 180 though. So when you are seeing a problem and you have to make 2 decisions in a row, you have to make a yes or no decision on the first, whatever characteristic it is. And then from the yes and from the no, you also have 2 more options for each of those, and it's branching off. That's kind of your hint that you should do a tree diagram. So let's look at the first example. John hits the snooze button on his alarm 60% of school days. So I'm going to start like this. Snooze. No snooze. If he hits snooze, there is a 70% probability he makes it to first hour AP Stat on time. I'm going to put OT for on time, and then I'll just put L for late. 70%, not great. If he doesn't hit snooze and gets up right away, there is a 0.9 probability he makes it to class on time. Much better. But he's still going to be late 10% of the time. Suppose we select a school day at random and record whether John hits the snooze button and whether he arrives in class on time. What is the probability that he hits snooze and is late for class on a randomly selected day? So hits snooze and is late. That is this path. So the probability of both of those things happening is 0.6 times 0.3, which is 0.18. What is the probability that he is late on a randomly selected day? Well, there's two ways that he could be late, right? It's the one we just looked at, but then there's also this way that he could be late. There's two different pathways. So we have to consider that first one. And we have to consider the possibility that he doesn't hit snooze and still manages to be late. It happens. And in total, we get 0.22. John sprints into class one day late as we are finishing the Pledge of Allegiance. Declan wants to calculate the probability that he used the snooze button that morning. So, given that he is late, what is the probability that it was a snooze day? So, out of all of the late possibilities, the 0.22, what's the likelihood he hits snooze? So on top, that's snooze and late, the 0.18. That's what we did first. And then on bottom, that's all of the ways that he could be late. And we get 0.8181, or 2. So if you know that he is late, it's pretty likely he pressed snooze. Not 100%, but it's pretty likely. So we know it's a tree diagram because we had that first choice, whether or not he pressed snooze, but then from each of those choices, it branched off again to on time or late. Okay, so this one here, I'll let y'all decide as a class right now. If you feel ready to try one on your own, you can do that, or you can just watch and I'll do it. So pause it right now if you want to. Okay, so Noah is running a cross-country race. He runs his first mile faster than 4:50, 40% of the time. And in the other, he takes it out slower. So I'm going to put fast and slow. 95% of the races where he goes out faster than 4:50, he finishes under 16 minutes. Which means 5% of that time he still finishes over 16 minutes. 32% of the time when he goes out slow, he finishes under 16 minutes. So sometimes he still is getting under 16 minutes. Just got to finish pretty hard. And then 0.68. So what is the probability that he runs faster than 16 minutes on a randomly selected day? Again, there's two ways to get there. So under 16 minutes, I used that word, okay. This is going to match what's in the diagram. That's why I'm changing it to under. So under 16 minutes, he could do that, or he could do that. Two ways to get there. So 0.4 plus 0.95, or the 0.6 plus 0.32. And I got 0.572. So what is the probability that he goes out slower than 4:50 for his first mile and finishes faster than 16 minutes? Okay, so he's going out slower and finishing under 16. So I just want to know the size only of that branch. So it'd be 0.6 times 0.32. We get 0.192. The end. So you guys can watch any part of this video if you want to go over it again. Remember, the key with probability is perseverance. There is a little worksheet for homework, and that's due in 2 school days. So since it's a Friday, that's not due until Tuesday. And we will see you all tonight for senior night at the football game. We're going to the football game right as soon as we get back from Hot Springs. So y'all have a great rest of your Friday.